Good afternoon, everybody, and welcome to TGIK number 90. Good to see you all. Who? Welcome, welcome, welcome. Let's see here. All right. So, I actually just discovered something interesting about YouTube. You know, it's always a learning process. I'm about 2 minutes late because I was actually talking to you all, thinking that I saw you. You were able to see me, but you weren't. So, I hope that you can all see me now. It looks like everything is streaming along wonderfully. So, if you can, give me a thumbs up. Good to see you all. We have who's with us today. So we got Waleed from, I'm not sure where Waleed is from, but he's definitely not far from sleep, probably. We got Martin from the Netherlands. We have me replying back that sleep is comes for us all. You know how it is. We have Lamati coming, joining us. Good to see you, sir. We have Rory in it for the long troll by giving us a name of the city that he's in that I think only Rory and maybe a few other people can pronounce. Lakola Head. I'm going to totally mess that up. And I can actually speak Hawaiian, so like I totally get the vowel thing, but you know these words like get me every time. Welcome, Shahar. Oh, I'm glad to hear that, Lamati. I'm glad that you really like the series. I'm definitely enjoying doing it, and I plan on doing quite a bit more with it. Right now I'm kind of working through the whole series of components themselves, and then I kind of want to move on to some of the higher level primitives, like what's actually happening in the API server. That's actually why I listed the API server last in the series. It's because once we get to that part, I want to kind of start going through things like the deployment and like really digging into like what a deployment actually does, talking about stateful sets and like when you pick them over other things, kind of digging into that sort of stuff. So I'm really glad you're digging it. And Shahar, also, I'm glad you're digging it as well. It would be a pretty neat book. I think that I struggle with whether it makes sense as a conference. I don't know. Well, I'll give that some more thought. Hello, Suresh from Hamburg, and Christoph from Dusseldorf, Germany, and Antoine from Paris, France. Good to see you, Antoine. And Vadim from Kiev, Ukraine, and Stevo from Germany, Leipzig, Germany, and Yaroslav from Sofia, Bulgaria. Such an amazing worldwide community we have here. You know, I just absolutely love it. Amin from Strasbourg, and Niren. Hello, Niren from Jersey. He's a good friend of mine. He works with me here at VMware. Super smart guy, and always like, you know, engaging in everything that's fun about the crazy changes that we see in technology. So super awesome. Welcome, Niren. We have David from St. Marie, Ontario, Canada. We have Yatin from Ashburn, Virginia, and Hap Lesson 2 from South City, California. I wonder where that is. Is that like South San Francisco, or is there actually a city called South City in California? I would not be surprised if there was a city called that. We have Gustavo from Brazil and Sean from Birmingham, England. It's very good to see you all. I'm glad you're all here. And in this episode, we're going to talk about Kube-proxy as a component. We're going to dig into like how it's deployed, some of the configuration stuff for it. Like we're gonna dig into that sort of stuff. Oh, South San Francisco, that makes sense. And then, but before we do that, we're actually going to like revisit a little bit about the kubelet that I meant to mention while I was on the call a couple of weeks ago. But you know how things happen. Got a little out of hand. We didn't get to it. So I definitely want to come back to the Kubelet API and show you where to kind of discover more information about it and that sort of thing. So we're gonna go back to that real quick, and then we'll move on to Kube-proxy. But before we do that, let's check out our notes for this week. So our notes for this week are up at tgik.io/notes, and you can find them there. Happy Friday the 13th, by the way. You know, it's odd. I think the numerology world just must be on fire this week because there's a lot of really interesting stuff that's happening, numerology-wise. I think, you know, inside of the world. So I did want to ask for the blessing of the demo gods as we go into this on this beautiful Friday the 13th. I think we're in good shape, but you know, you never want to be too overconfident, right? Like you want to think that there's always like room for variation there. The next thing we have is this really like neat thing, the numerology stuff. It's Palindrome Week here in the U.S. It's not Palindrome Week in other parts of the world where they order their dates a little differently. Like some parts of the world we do month, day, year, or that sort of stuff. But here in the U.S. we do month. Oh, sorry, the other way around. We do day. Yeah, you get the idea. Some places do day, month, year. We do month, day, year. So September 10th through September 19th all represent palindromes. And the neat thing about that is that there are 10 palindromes in a row, 910 through 919, and that there's actually as many letters in palindrome as there are days that qualify as a palindrome here in the US. So I thought that was amazing. Yeah, we have a full moon on Friday the 13th as well. So, be careful out there. There's all kinds of, well, I guess, I'm not going to put my superstitions on y'all. I just thought it was interesting. Other interesting stuff happening this week. Kube 116 has been bumped to September 18th. There's a lot that's been going into Kube 116, and including API removal. You've heard me talk about this. I did a whole episode on it a couple weeks ago, and I highly recommend that anybody watching this video take a moment and understand what I'm referring to when I refer to API removal. Remember that some APIs that you may be taking for granted are about to change, and they will no longer work the way that you expect them to. And this will happen in very insidious ways, because there'll be manifests that you have always just applied to Kubernetes that worked, and now there will be manifests that do no longer work. Is it weird that, yes, it is kind of, but what would the word be if you were going to have palindrome as a palindrome? I'm not sure. Anyway. But yeah, so API removal in 116, super, super important. I'm reminding you now, and I'll remind you again, and we'll talk about it some more. API removal in 116. So just to give you a link to that real quick, because, the title is Deprecated APIs, but it's actually API removal in 116, right? So these resources, network policy, pod security policy, daemon set, deployment, stateful set, replica set, and ingress will all be moving around in the API. The older versions or the older API references for them will no longer be served by the API server, which means if you try to bring up a deployment using extensions v1 beta 1 or apps v1 beta 2 or apps v1 beta 2, 1, that deployment will not be accepted by the API server, because that object is no longer known by the API server. You have to use apps v1 for daemon set, deployment, stateful set, and replica set. I'm actually more worried about deployment and apps v1 than I am for most references, because I think that quite a lot of people out there working with Kubernetes are going to be surprised that it doesn't work the way they expect. It's an easy fix, but just be aware. Spread the word. Help me spread the word about it. All right. Enough on that subject. Let's move on. What else do we have? So 116 got pushed a little bit, mainly because of the amount of work and a lot of amount of change that's happening. So they just want to make sure that it's a really good release. So they're pushing the date out a little bit. The release will be a little bit later. This is information about what the patch release process is. This is where you can actually find information about the timelines for things, all of the stuff that's come along, what the cadence is, and who to contact, and all that good stuff. Medium, what can you do? The mistake that cost thousands, Kubernetes GKE, lessons learned about scaling Kubernetes clusters. Man, this looks pretty intense. Let's see what the mistake that cost thousands was. So, what is the difference between a Kubernetes cluster using 100 N1 standard 1 CPU VMs versus having 1 N1 standard 96 CPU versus 6 N1 16 CPU? I asked this question multiple times in the Kubernetes community. No one suggested an answer. If you are unsure about the answer, then there is something for you to learn from my experience, or to skip. I answered. The premise: I woke up in the middle of the night with a determined to reduce our infrastructure costs. We were running a large Kubernetes cluster. Large is relative, of course. 600 vCPUs. Invoice was $3,500 a month. We used expensive data center. We used different types of machine. We used horizontal pod autoscaler. We use cluster autoscaler to scale node pools, and we use preemptible VMs. Using exclusively preemptible VMs, kind of similar to spot instances in AWS, they were able to lower their cost even more. Major red flag about that nagging feeling. Average CPU on the node was 10 to 20%. This didn't seem right. My first thought was that I had misconfigured compute resources. I'll illustrate my mistake through an example of a single deployment. Pods that average 5M idle are idle. This is a task in the queue for them. A minute later, a bunch more CPU work. Looking at the above, I thought it makes sense to have a configuration such as, this translates to idle pods don't consume more than 20, and active healthy pods peak at 200 meg, or 200 microshares of a CPU. However, when I used this configuration, it made the deployments hectic. So it never happened whenever a new node was brought in and out of the cluster, which happens often due to autoscaling. As such, I kept increasing the requested pod resources until I ended up with the following. Okay, 250 to 150. With this configuration, the cluster was running smoothly, but it meant even idle pods were pre-allocated more CPU time than they needed. I actually wonder what the application is, like if it's Java or some of the other things. All right, back to the answer. Back to my question, sorry. What's the difference? Retrospectively, it was an obvious mistake. Distributing pods across nodes with a single vCPU does not allow for efficient resource utilization as individual deployments change between idle and active states. Put another way, the more vCPUs you have on the same machine, the more tightly you can pack many pods because the portion of the pods go over their required quota. They are readily. I'm also a little bit worried. I'd be leery about this also because I know that Go is like, got a lot of like really good multi-threading capability, and so I'm very curious, like, because the platform that you're leveraging, Kubelet and things like that, actually are written in Go, whether like a single CPU would actually end up biting you pretty hard in that way, right? Because you couldn't distribute the work across more CPUs, especially as you added more pods and those sorts of things. So that would make me nervous. I would think more vCPUs or some balance between vCPUs and memory or I/O would actually be where you wanted to head. So in this case, they went to 16 vCPUs. It's an interesting article. I mean, it's an interesting experience. I'm sorry that they did that in production, but definitely an interesting study into what's happening there. Patrick Lang, who I am proud to say I'll be doing a workshop with at KubeCon this year. I'll be working with Patrick Lang, with James Munnelly, and with Mr. Benjamin Elder. We'll be doing a workshop into how to kindly, or to use kind to do development against the Kubernetes codebase. So definitely check that out. But Patrick Lang is like our Windows is like the it's like one of the senior software engineers at Microsoft, working really closely with like what's happening with Windows Server containers and those sorts of things. And so I'm really glad to see him out there talking about that stuff. If you're interested in Windows and containers, follow that guy. He has a lot of really good information, and he's doing a lot of work around it. So highly recommend checking out this podcast, and if you're interested in Windows containers. Let's go back to our questions. Let's see, who else do we have here? We have Kieran from Hyderabad. We have Yanislav. Tell me about the full moon in Europe. We have Fully Geared Bear from Porto, Portugal. And we have Bogdan from Romania. We have Amin from Algeria. And Amin is a network engineer. Welcome, Amin. I've done some network engineering myself. Welcome, Robert from Dublin. Good to see you all. All right. What else do we got here? We have the Cloud Native Survey. This is actually a survey that I believe, CNCF Cloud Native Survey, was put out by the CNCF. And it tries to take a pulse of those that are actually making use of cloud native technologies. Help us get this survey out there. It's really great to have people do it. There's an opportunity to enter to receive one of three $200 Amazon gift card prizes, and we really use this information to kind of help inform. I have no idea when my video will be available. Yes, they are. They are, but they take a long time to post. Like if you go to the YouTube channel for Black Hat, there's like a huge number of videos that are available for free, but they always like take a few months to actually go out. So I'm actually looking forward to seeing it myself, even though I know I will sound like a chipmunk. I'm still looking forward to seeing the video. We use these surveys to understand better how, what the areas that people are really focusing on, right? Like one of the things that I actually really got personally out of the last survey was what CNIs were people using in production, and like whether that was changing over time. And so there's a lot of really great questions in here. Please feel free to spend some time answering them, and help, again, help us spread the word, get them out there. We have somebody. Oh, stop. Okay. We have Cruise, which is a car company, a self-driving car company, working on open sourcing Isopod, an expressive DSL framework for Kubernetes configuration. After, I mean, this week the Twitter sphere was again kind of throwing fuel on the fire around YAML and some of the other stuff. And I mean, I know that there's obviously always room for improvement in all of these models. And so it's great to see other people out there trying to do exactly that, right? Like improve the user experience. I find that, like, for my own personal part, I don't think that there is a perfect answer. Let that be said, right? I feel like there's going to always be some mitigating factor or some overriding factor that like is going to be the thing that enables your team to approach a tool and be successful with it, right? Now, whether that means you go the Pulumi route, where you decide to, like, actually, instead of learning the overhead of learning an entire new language, something like JSONet or KSONet, you want to basically just extend your knowledge of an existing language like Go or Python and into the domain of handling infrastructure, right? I think that's actually a pretty interesting play, and that's the bet that Pulumi's making. But there are a ton of things out there. That are actually trying to solve this problem. And this is a new one. So these folks have actually made iPod, what do they call it? Isopod. I'm glad they didn't call it iPod in retrospect. That would have been confusing. So Carl Eisenberg described how the PaaS team was building a multi-tenant compute platform on Kubernetes to support hundreds of engineers. In this blog, we explore the challenge of configuration management in Kubernetes and present our open source Isopod as a distinct solution. Well, I mean, check that out if that's something that is interesting to you. It's like they're working on templating. I'm not going to dig into it at this time, but definitely check it out if it's interesting to you, and then give us feedback. If you think it should be an episode of TGIK, let us know. All right, it's t-shirt time. From now until KubeCon, Cloud Native Con in November, I will give out Kubernetes t-shirts to people on this forum who are helping new users and contributing to the community. So feel free to dive in. I'll be using a mix of secret criteria to determine the prizes, and I will be giving them out. This is Mr. George Castro that I work with here at VMware. He's one of the community leaders inside of Kubernetes, and he will be basically rewarding people who are actually out there trying to do their best and help others to succeed with Kubernetes and technologies like it. So if you jump into the forums and help it out, basically this is discuss.kubernetes.io. He's trying to motivate people to jump in there and do that stuff. So yeah, I mean, if you got time, do jump in and help. It'll be great. What else do we got here? We have a webinar for Octant. If you're interested in asking questions or you're interested in just seeing a demonstration of it, check out the webinar. There's a link in the notes for how to do this. And speaking of webinars, it's my last news article. Did you know that CNCF does webinars? And there are quite a few of them. And so if you're interested in learning more about the space or about different technologies, definitely check out the webinars that are available at cncf.io/webinars. There's a bunch of them that are coming. One of the ones that actually happens on a pretty regular basis is this one that's called What's New in Kubernetes. I highly recommend that because it's actually, usually it involves the release lead talking about Kubernetes, and what they do is really dig into the detail about like what new stuff has come in 1.16 and the kind of sharp edges, the things you have to be aware of before you migrate to it, that sort of stuff. So definitely check that out. All right, that is all the notes. Thank you for putting up with all of the nodes. I mean, it really doesn't seem like it was that many nodes, but it's like, you know, it took a little while. Here we are. Let's go back to the notes. I wish I knew when my Black Hat talk would be available. I keep looking. Duffie says, when you get to the main topic, can you give us your thoughts on Cilium? I like Cilium a lot. They just came out with a new release, and one of the selling points is replacing Kube-proxy. I like that they replaced Kube-proxy a lot, but we'll talk about it a little bit more. Rory McCune, yeah. I mean, Rory makes a pretty good living at security, you know, so I think that's good for him. All right, I have unchecked this box where it says Kubelet API because I was realizing, you know what, I didn't really spend as much time on the Kubelet API as I should have. And so to address that, what I'm going to do is show you where in the code base you can find information about APIs that are expressed by things like the kubelet. So here we are at GitHub, github/Kubernetes/Kubernetes. And I'm going to talk just real quickly about kind of like layout for things, which I think is kind of, you know, it may be useful to you. You may have seen this before, and you may not have seen it. But the way that things are kind of built, you know, the core components within Kubernetes are built. There's actually like a command directory, CMD directory, in which you can see all of the components that make up some of the shared components, and actually all of the many of the other components that are like in tree for Kubernetes and things that we build. So some of these are generators, things that are going to generate kube docs and generate manuals and Swagger type docs and all kinds of other generators. But we can see that we also have like the main components, kube scheduler, Kube-proxy, kube controller manager. And if we dig into, and kubekettle, of course. And if we dig into kubelet here, we can see there's really not a lot underneath this directory, right? It's mainly the configurable surface. It doesn't really get into the actual code. And then you might be thinking, okay, well, that's interesting, but where is the actual code that represents the kubelet? Well, it's not going to be under the command. That's kind of like your entry point. That's why the configurable surface is actually exposed there. What it will be under is under package, PKG, which is a different directory, which represents actually like where most of the actual code represented for many of these things are going to be exposed. So if I go underneath Kubernetes package kubelet, then I have all of the code that actually represents the kubelet itself. And and if you're interested in digging into it more and understanding what's available, this is a great place to kind of like, if you want to just go read all the kubelet associated with the kubelet, this is where you would go. Most of the things within Kubernetes that have an API kind of express those APIs in a single place where they try to like make them available to people who are so that they can be understood. And if you look at projects like KubeADM or Kind, they kind of express it in the same way, right? They basically will try to put all of their APIs underneath the APIs in a way that they can actually be, in a way that they can be well understood from that perspective. What I wanted to show you was this one, which is basically the API for, no, that's not the one I wanted. Let's see. I believe I want pod resources. So it's a gRPC-based API, but there's actually more to the API than that. Because the API server, because the kubelet actually has an API that it expresses through like a get pods interfaces, get devices, these sorts of things. And so what I was looking for is that API pod resources v1 alpha 1. I think I actually might have to come back to this again, because what I was looking for is not super easy to find, unfortunately. Okay. Well, let's do it this way then. So yeah, I'm gonna have to come back, maybe. That's the client handler. What I wanted to see was the serving interface and like what was actually being exposed via the API inside of this space. And I think that unfortunately, I thought that it was going to be under APIs because that's where I find it in other projects, but I don't see it here. Package server, package kubelet server go. Let's take a look. Show package server go. That might be it. So package kubelet server go. Package kubelet. Thank you, Rory. Server. All right, here we are. We're defining handlers. That's what we're looking for. And then there'll be something that actually satisfies things like paths, where you can see what's being exposed. So obviously we know about the cAdvisor piece. We talked about that one last time we were walking through what was here. We know about the health Z endpoint. Here we go. Yes, this is what I'm looking for. Okay. So install default handler. This install default handlers piece is what I was actually trying to get to, so that we can understand like what paths were exposed by the kubelet, right? And so we have a slash paths, and we can describe actually like what's actually going to happen. So it's going to produce this. It's going to do a get pods, and we can go look up the function for what that operation actually is. And we can understand that it has a custom metrics or metrics endpoint, and we played with that one last time. The cAdvisor, we have a debug pprof endpoint. We have a slash run for basically starting the cAdvisor or starting the debug handler. All of these paths are exposed by the kubelet. Now, and we have port forward. So a lot of the information, a lot of the configuration that is described or that you can do to the kubelet or to any given pod on a kubelet, things like execing into them, things like forwarding a port to them, things like copying files back and forth in and out of them. These are all actually expressed by the API associated with the kubelet itself. So for example, the workflow to do, oh, actually, that's one thing I should show you real quick. Because there was a great blog post, I think that Joe mentioned it on his TGIK last week, that really does get into the code of how kubekettle exec works. And I think he does a tremendous job on how that actually works. But it talks specifically about how the mechanism works, right? So like if you on any machine, like from your laptop or what have you, and you type kubekettle exec into a particular pod within Kubernetes, that call will then go to the API server. Let's go down to the bottom graph. That pod will go down into the API server, and then it will be forwarded to the kubelet related to the pod that you're trying to exec into, and it will actually attach to that pod by proxy, right? So the API server will proxy that call to the kubelet via that kubelet API that we're looking at over here, right? So this Kubelet API that we're actually looking at is actually going to describe like what calls are necessary to describe things like exec and those sorts of things, right? So we can do things like get the running pods. We can do things like get the logs of the running pods. There's so many functions that are exposed by this API. What the pod ID is trying to get information about how to actually route back to a given pod. Getting the running pods. Yeah, I mean, there's quite a lot of, here we go. Here's the exec request params, right? So the actual parameters necessary to exec into a container, because you're actually going to hit one of the containers within a pod, it needs to know how to actually populate that. And here it is specifying what the required params are and making sure that it gets that information, or it will just reject the request out of hand, right? So all of this is represented by the API exposed by the kubelet, and that's what I wanted to actually talk about. Yep, and you're right, Rory. This is exactly where it was. Mr. Dims, are you raising your hand because you have a question? Or are you just saying, preach? I can't really tell. I'm hoping it's preach. I guess we'll see. Or are you saying hello? Hello, Mr. Dims. All right. So yeah, the kubelet actually has quite an extensive API that it exposes to the API server. And for most of our normal day-to-day use, we never really see that, right? But we're never actually, we don't interact with the kubelet directly. Most of the time we interact with the API server through exec calls or log calls or attach calls or those sorts of things. And the API server interacts with the kubelet on our behalf. But what I wanted y'all to think about was when we were talking about the kubelet last time, is that to remember that the kubelet is doing so much more of the heavy lifting in this picture than we think perhaps than we generally tend to think that it does, right? Like when you exec in, the API server is going to handle authentication, authorization, making sure that you have the permissions to do things like exec into that pod. And then it's going to literally proxy that connection over. It's going to hand that connection over to the kubelet responsible for that pod and let you handle and let you go through that whole exec process. And then once the connection terminates, it's going to handle the cleanup. But the API server isn't doing much other than just like orchestrating the proxy to the kubelet that is responsible for that work, right? It's actually handling all of the authentication stuff. It's handling all of that bit, and it's also handling the proxy piece. But when you're interacting, when you're typing commands in and out, right, those commands are actually happening inside of the container via a proxy connection back to that kubelet. And that's what I was trying to express by the Kubelet API. So if you ever really want to just like introspect and see, okay, like what all can the kubelet do? What is that API represented by? This is a great place to jump in and kind of like look at how that is. So that path, again, I'm just going to put it in the notes so I don't forget. Kubelet API. All right, so the Kubelet API is expressed in server Go, and that's where you can find it. And that's where you can find things like the definition of what configs d and metrics and / running pods and / attach and all of those things are. That's the last thing I wanted to talk about the kubelet before we move on to Kube-proxy. All right. So thank you for putting up with that. That was the last bit of the kubelet. And now let's move on to Kube-proxy. I'm going to clean up my tabs here a little bit. I was actually just talking to some friends recently and we're saying, we're saying, okay. They were saying that they never like remove tabs, and I was like, huh, wow. I want to copy this one in too before I forget. We'll put that one under theory of operation. So definitely check that out. All right. So the next up in the series is Kube-proxy. We're going to talk about like how it works. We're going to talk about how it authenticates to the API server. We're going to talk about the different models for Kube-proxy. We're going to talk a little bit about services, theory of operation, config-ity, and metrics. So let's jump into that. All right, so here's what I've got going on today. I have two Kubernetes clusters that I've created using Kind. And these two Kubernetes clusters are configured in each of the two different ways that you can configure Kube-proxy. Well, two of the ways, I guess the two modes for Kube-proxy that are available today. I think actually there used to be 3 modes. There was a user space proxy as well, but I think that's finally being deprecated, and I suspect it'll be removed. If it's not already removed in 1.16, it'll be going away soon. So there's really only just the 2 modes that remain. There's IPVS and IPtables mode, and we'll talk a little bit about what those mean. But before we do that, I wanted to bring up the reference doc for Kube-proxy. So this is our reference doc for Kube-proxy. Give it a read. It's a very interesting component within Kubernetes because it does quite a lot of work managing the service abstraction within Kubernetes. I'm hoping that many of you already kind of know what services are, but we're going to talk a little bit about them. But like what they do and those sorts of things. Here are the flags that are available within Kube-proxy, like some of the configurable mechanisms that are in here. And we can talk about some of the things that they work through, but we're going to give this kind of like a good overview here. So yeah, quite a lot of flags exposed by it, including things like the hostname override string. We'll talk about that one. That was an interesting one. And we'll talk about also just kind of like general service configuration. Okay. So definitely worth reading this. I'm going to link this in so we don't forget. Let's break down auth to the API server. How does Kube-proxy authenticate to the API server? And does anything try to interact with API with Kube-proxy directly? So the first thing I wanted to talk about when we talk about Kube-proxy is kind of like how it's deployed and kind of help kind of express that a little bit. So I'm going to move into my IPtables cluster here. This is the default configuration for Kube-proxy today. I think it might change in the future, but I feel like we've actually discovered what we need to know to be able to change it. Okay, pods-a. So we see Kube-proxy running here on each node. We have one running on the master and one on each of our workers, or one on our control plane node and one on each of our workers. But the way that it's deployed is kind of interesting. So if I do a kubectl describe or get ds-n kube system, I can see that I have 2 daemon sets deployed, right? One that's actually handling the network CNI piece. In this cluster, I was using Canal, and also a daemon set for Kube-proxy. Now, it's an interesting question. Why use a daemon set? Or like why is that primitive daemon set interesting in this, or the right thing for this particular case, right? So let's look at that daemon set real quick. Describe ds-n kube system, Kube-proxy. So here's our daemon set, and we have a selector that says, a node selector looking for any version of Kubernetes running Linux, like presumably because if there's a different operating system, we would want to actually make sure that we deploy the correct version of Kube-proxy for that other operating system. We have the desired set of nodes, which is all of the nodes in our cluster and the up-to-date. We have things like, here's some things that are actually used to configure by Kube-proxy to implement the configuration of IPtables and those sorts of things in the underlying host. There's some really interesting mounts for Kube-proxy, and so let's just talk through those. So we are actually passing a config file to Kube-proxy to configure it, and we're also passing this hostname override flag to Kube-proxy. This was actually an interesting thing that came up, I guess a few versions ago. I think it was like 113 or some such, like why the hostname override is so important. But it is a very key component when configuring Kube-proxy, and we'll talk a little bit more about why that is. These mounts that are expressed into the Kube-proxy node, this means that like this is a pretty high value target for somebody like building Kubernetes clusters, because if you think about it, this is going to run on every node, and it has access to like the lib modules directory. This is where your kernel modules are, right? The reason it has this is because Kube-proxy might be the first thing that is trying to start up IPtables. And if it is the first thing to start up IPtables has a mechanism by which the very first time somebody runs IPtables commands, it will auto-load a lot of the kernel modules necessary to support that. And that's all fine, except that when that auto-load happens, you have to make sure that the auto-load is actually, the IPtables command has access to the correct directory where those modules are. Otherwise, it might load modules that may not be compatible with the underlying kernel. That's why you want to mount like lib modules from the underlying host. Very good reason to have that there, but at the same time, this means that it's kind of a high priority target for things that are trying to secure Kubernetes, right? Because it means that like we have the ability to, like, I guess it's read-only mount, so it's not quite as bad. So read-only mount means that like at least those modules will only be mountable from in there. But remember that we also have to give permission based on to load those modules into the underlying node. So permission-wise, this is still pretty interesting, a pretty interesting target. We have Xtables lock, which is really about basically making sure that we don't stomp on ourselves when configuring IPtables. IPtables is not atomic. When you're configuring IPtables, it means, what I mean by not atomic, if you worked with IPtables over time, you might think that you can inject a new rule, and that new rule represents just an atomic command. Like I want to add one more IPtables rule, and it will happen, and then we'll get injected, and then everything will be fine. But what really happens under the cover is, because of the way that IPtables was originally designed, is that it literally has to drop the entire configuration for IPtables and reinstantiate the new entire configuration of IPtables. It's not atomic. Interesting stuff. And so what Xtables lock kind of allows us to do is make sure that we're like, you know, hopefully there's only the one writer. Now, not everything respects Xtables lock, but there should only be the one writer against IPtables. In reality, or in practice, I should say, there are usually actually quite a few writers to IPtables inside of Kubernetes, because you have things like the kubelet configuring IPtables, you have Kube-proxy configuring IPtables, and if you have a CNI implementation that is going to handle network policy, that network policy is also going to be implemented in IPtables. And so that's actually quite a lot of cooks in the kitchen when you think about it. There's a lot of rewrite that has to happen globally to IPtables because of that. Yeah, we should talk about that. That's a good point, Nicholas. Some implementations of Kube-proxy actually use these as a static pod, so similar in some ways to the API server, controller manager, those things. All right. What other things about this configuration are interesting? It has a priority class of system node critical, which means that it has to run inside of the, I believe that means it still has to run inside the Kube system namespace. And our goal with that priority class is to make sure that other things get evicted before Kube-proxy. Lamati, yes, that is the correct answer. NFTables does solve the problem, but at the same time, I said I wasn't going to get into this. But at the same time, it actually represents another set of, another series of problems. I'm going to give a quick overview of that, and then we'll move on to other stuff. So, NFTables does actually address the problem. The interesting thing about NFTables is that they're trying, obviously, to make it so that users of IPtables have a pretty fluid experience in moving between the different kernel modules. Now, what's interesting is that the way that they went about that was not in normalizing the ABI as it is represented by the kernel interface. Instead, they normalized the API as it was represented by the binary, right? So I can use IPtables in the legacy mode, in which I'm actually using kernel modules associated with the original IPtables implementation for that particular version. But if I wanted to move to the NFTables implementation, I could actually, I would use the same IPtables command, but I would have to check out the new version of that command that allows me to interact with the NFTables kernel module, not with the IPtables kernel module. Because of the way that's all panning out, if you think about the way that the way that we containerize this stuff really represents some interesting challenges, right? Like as we move forward, we have to think about like those distributions that are moving from legacy IPtables to NFTables, and we have to make sure that the binary that is exposed by Kube-proxy in its container is actually binary compatible with what the underlying host would use to configure IPtables. Because what if the host got installed and you ran some IPtables, you've got some like default rules that you've got defined, and when you did that on the underlying host, you brought up the NFTables implementation, because that was the version of, that was the implementation that was chosen by the distribution that you picked. Say it's like Debian Buster, for example. And then you deployed Kube-proxy on that node, and the Kube-proxy binary, IPtables binary that Kube-proxy uses, isn't actually binary compatible with what the underlying node uses. Now at this point, Kube-proxy is not going to work. It's not going to be able to actually interact with IPtables in a useful way, because there's going to be that mismatch between the two APIs. And this has actually come up in the community, and this is something that we're working on trying to resolve. And I feel like there's actually quite a lot of thinking in a lot of different directions about how to go about fixing it, but it is an interesting problem in the space, especially as you think about how containerization and the underlying node configuration happens. I mean, in this case, the real challenge is that like Kube-proxy is an implementation of configuration that is specific to the node, like a node runtime. But we're trying to implement that by using a container, right? Most of the time, if you're going to implement configuration at runtime on a node, you might use something that exposes the node itself, right? Some configuration management tool like Ansible or Chef or Puppet, where you effectively have some code that's running in the system set of network name, the system set of namespaces, and has the ability to configure that at runtime. In our case, we're trying to do this inside of a container, and so it really represents a very interesting problem. From your text to the ears of whoever is in charge of all of that, I would love to see BPF be the long-term solution, yes. But I feel like we're a little further away. Ask me again about Cilium, though, because that is the answer, in my opinion. I feel like they're in a much better position to actually solve this problem than a lot of projects are, because they're able to take effectively that entire space and solve it in a much more reasonable way. All right, so a lot of information about IPtables, a lot of information about what Kube-proxy does. I want to get into kind of generic, a little bit more about why daemon set. So let's come back to that original question. So it's a daemon set because we want to make sure that as you add more nodes or remove nodes, well, specifically as you add more nodes, that we ensure that Kube-proxy runs on every node. Now that in itself is kind of interesting. That means that every node within your cluster, right, is going to be running Kube-proxy. Now, this is actually one of the things I really dig about Kube-proxy. This is an interesting thing, right? So Kube-proxy, that means that it represents a distributed system, but maybe not in the way that we normally think about it, right? So as we add more nodes, we add more Kube-proxy instances, and each of those Kube-proxy instances in the current design before endpoint slice has a view of the entire list of endpoints and the entire list of services, right? So if we do kubectl get svc-a, it would have a view of all of the services defined within the cluster. And because Kube-proxy is responsible for implementing those services, each of the instances of Kube-proxy is responsible for having a watch for all of the services defined within the cluster and implementing them for the node in that Kube-proxy's control. But what I mean here is, if I have 1,000 nodes, each of those 1,000 Kube-proxy instances is configuring IPtables on a given node as they see and understand the state of services for all of the services within the Kubernetes cluster. This is consistently configured on each node cluster-wide. And the thing that is implementing that is Kube-proxy on the host. So as I add a new, actually let's do this. As I add a new Kubelet create, run Nginx, images, Nginx. So as I create more services, right, in this case I actually just created a service of type cluster IP. As I create more services, each of the Kube-proxy instances in my entire cluster will become aware that that service has been created, and then it will have to effectively translate the configuration of that service in some useful way to each individual node's configuration at runtime. Let's take a look at what that means in each of our two different clusters here, just for a single node. And then we can talk about, like, because what I'm trying to get to is, like, I want you to understand that this is really fascinating because it means that configuration may be unique on each node, but only because of timing, right? Like how long it actually takes for each node to understand the entire configuration of that service set globally has to be done on each node specifically. So if we jump in, I'm in the IPtable side. Worker bash, IPtables save. So here are the IPtables rules that were created for this Nginx service, and we can kind of see like what was actually like what it did here. It made a service that said if you're coming from any of the pod IP addresses in the entire cluster, and your destination is 10.103.43 or 42.17, which is the IP address associated with this cluster IP, then I want you to go ahead and forward. I want you to modify the destination port to port 80 and then forward it to mark mask. And then later on, if the destination, regardless of the source, is headed for 10.103.42.17.32, again that cluster IP, then I want you to send it to this service. Let's take a look at that service. So we have a new stanza within IPtables that describes that service, right? If the destination is that, then I want you to comment it, cluster IP port 80, and this is actually the line that we saw before in the Kube services output. And then we do this kind of crazy thing, which is mostly pretty cool. We do this kind of crazy thing where we basically try to randomize across the known entities or the known backends for a particular service. And that's actually where this kubeset piece comes in, right? So if I do the same command, but I pull up that target, what I can see is that right now, that's interesting. That right now it's actually forwarding that, let's do this. I think actually that there should be more endpoints than that. kubectl get endpoints dash Nginx 10.2.44, 1.2, and 2.2. Did I miss that before? Yeah, so why don't you see 1.2 on there? 1 second. What I'm going to do is pull up the entire IPtables set so that we can look at it kind of interactively here. Hack the planet. Exactly. All right, so Nginx. So here we are saying if the packet is not coming from a pod IP, modify the destination port to port 80 and send it to kubemark-mask. If the packet is the destination IP of the cluster IP, then jump it over to this guy. So static mode or statistic mode random probability 0.50 between these guys. Oh, there it is. Okay, we are, okay, sorry. So we do only see those two, we do actually see all 3 entries. Well, those 2 entries. So if the destination is coming in here, then and the source is, so there's our 10.1.2.80, and there's our 10.2.2.80. I think this has changed recently. We have 2 targets. We have kubesep and we have kubesep for MQW. So we're actually, in each of the cases, we're randomly deploying it across the 2 FPTO. So we can see why IPtables is a little tough to read, right? Like there's actually definitely some challenges in understanding like what's going to happen with the packet when we send it out, right? So we see the destination being this 4N5, and if we look at that one, we can see that it's going to balance. It's going to send 50% of the traffic to this endpoint. And that it's also going to balance, I think it's actually just going to send all of its traffic to that because the other one doesn't look like it's getting triggered correctly. Could one abuse Kube-proxy to specify a certain external proxy for specific domains as well? Kube-proxy is really not going to look at the name per se. It's going to look at the IP. I mean, you could do interesting things, probably not with names per se within IPtables, but you could actually overwrite the rule set within IPtables for that sort of stuff. All right. So let's take a look at how this is actually. So what we're seeing here is that, the theory of operation here is that it's going to balance its traffic kind of naively across all of the endpoints within the within that endpoint, within the Nginx deployment. So again, if we go back here and we do kubectl get endpoints Nginx, we see that we have 2 pods ready. We have the only 2 pods that we created. 10.244.1.2 and 10.244.2.2. They're both listing on port 80, and that the implementation of Kube-proxy using Iptables mode within that kubelet, or within that particular node, is going to actually handle the forwarding of that traffic, right? So if I do curl, actually, you know what, I'm probably going to want to do something else. I'm going to do kubectl delete edit deployment -n kube nginx. Instead of using nginx for the image, I'm going to use a different thing. Inanimate echo. Okay. So Docker exec TGI IPtables worker 1 bash. We still have our configuration here. I'm going to grab the IP address that is associated with that cluster IP, right? And I can do that also just by doing describe svc to nginx. And here's our cluster IP, 10.103.42.17. And I'm going to do curl okay, and then we're going to do grep for what I want to see is the IP address of the node. Grep for 10.244. And so what we're seeing in this output is that the traffic is actually balancing back and forth in a pretty naive way across the two endpoints defined within the cluster, right? And so in our grep here, what we're doing is we're trying to understand which of the two pods we're aimed at, and we're able to determine that from the host file. So we can see the IP address. We have two nodes that are running, or we have two echo servers running, and we can see that we're balancing back and forth between the two of them, right? In some cases, we're using 10.244.2.3. In some cases, we're using 10.244.1.3. Now, here is another thing that is interesting. Is there a source IP in the output here? Requesting IP. So this is interesting. And this is actually also something I kind of wanted to share with you because I think that Kube-proxy is also responsible for doing some of this work, right? What we can see is that when we go back and forth between the two IP addresses, grep. Don't hate my bashisms. I know you don't, but still. What we can see is that when we go back and forth between the two IP addresses, we're seeing a different source IP address used when making the call. Now, this is kind of an interesting point, and Kube-proxy is responsible for this. Yeah. But what I wanted to point out was effectively what I mean by a very naive load balancer, right? So although we can see the connections going back and forth, we can also see that the source IP address changes. And this highlights one of the important things to understand about Kube-proxy, and that is that it is very naive in the way that it's making the routing decision. Right now, I'm connected to the worker where one of those Nginx, or one of those CRI get pods, where one of those Nginx instances is running. But instead of always sending my request from this host to the local Nginx, it's actually balancing that traffic across the existing Nginx instances, right? And when I do forward that traffic to a different host, it means that my source address is going to be the IP address of the node. But when I send that traffic to the one that's locally hosted on the node that I'm on, it means my source address is going to be the IP addresses within that network range. And this also works on the outside, right? If I do, let's see, kubectl get, let's do kubectl expose -n kube system, actually, nginx port 80, target port 8080. That's probably the way you get to do what I want, but what I'm going to do here. So now I've created two different services. One service that's actually using cluster IP, and one service that's actually using NodePort. And if I do kubectl get endpoints for Nginx, I can see our two are backend services, and for NP, I can see our two backend services, both resolving to the same IP port pair, right? Now, what I wanted to show you was this, right? So now I have a NodePort exposed, and Kube-proxy is exposing them. If I do curl minus 172.0 kubectl get node -o wide. So this is actually the IP address of the service exposed, the IP address of a node where this actual service is exposed. I can connect to any of the IP addresses of any node and get to this service. But to show you that, actually that's done. I'm going to hit that service port, the node port that we exposed, 31962. And I can actually hit any of the nodes. So even if the node is not resident on that host, I can still hit it, right? But we can also see from our testing that the IP address changes, even though we're still hitting that same node. And the source address, whoa, what is all that? Oh, that's a bug. Neat. We're going to have to come back to that. All right. So I can actually jump. So let's grab. egrep requesting 10.244. So in our case, you can still see that the source address is changing, right? When we go back and forth between the two hosts, we're bouncing back and forth between the two requests, right? Sometimes it's using my local IP address sometimes it's using the IP address of the node that I connected to actually handle NodePort, and sometimes it's using the IP address of the locally relevant one. So it doesn't matter where we come at, it's still going to change the source address. Exactly, Bogdan. You're like reading ahead. Look at you, like setting up. All right, well done. All right. So what can we do about that, though, right? Like we can actually we can change that behavior a little bit. But we did actually. But I wanted to make sure that we, that y'all get the idea that what's interesting about this configuration is that each of the instances have their own complete view of all of the services that are defined. And they're not configured specifically consistently, right? So if I do Docker exec ti IPtables worker, and then I do IPtables save grep nginx, and I do the same thing with worker 1, or 2, sorry. They're configured consistently in that they're operating with the same information, but the ordering of these things might also be subtly different, right? And as we increase the number of instances, kubectl scale. Actually, you know what? I want to do that. I want to do deployment nginx replicas 4. So as we scale the number of instances, we're going to see this information change. But you have to jump in a little early, jump in a little further. Grab. Okay, because now we have more instances. And we can see that in this particular case, the probability is a little different too, right? Because we're actually sending it off to different targets depending on a probability that's been defined at service definition. And if I compare that output to worker 0 or worker, I can see the difference. There may be different output. So actually, in this case, they're all consistently configured, which is pretty rare. Like usually one of them will pick like a higher probability for a different result, but in this case, it's actually matching up. So random in this case is not quite as random because it's actually balancing out pretty equivalently. But the configuration of each node is actually for each Kube-proxy instance is responsible for configuring the services as they are defined or as they are understood by each of the Kube-proxy instances and their watch against all of the services and all of the endpoints within the cluster. That's right. Well, I mean, yeah. So the internal representation of the API server, right? kubectl get svc. There is a Kubernetes service that is defined. Same thing for DNS. There is an internal cluster IP service that represents the API server, for Kube API server, and those are going to balance across all of the actual control plane nodes. If there's only one control plane node, it will only target that one thing. Right? In our case, it will only terminate on the one node where the API server is running. This is a single master cluster. But if I brought up like a 3-master or a multi-master cluster, then it would see all 3 of those hosts and balance across the set. That question was asked by Glenn. So let's get back to Bogdan's question, because I think it's actually very important, and it actually relates specifically to the whole NodePort service thing, and it also talks about kind of the way that Kubernetes actually manages that. So let's look up external traffic policy. These documents I think are actually really good to read when trying to understand what Kube-proxy is doing and like the problems that it has to try and solve. Theory of operation. Okay. What these say, what this is talking about is the source IP address as it needs to be configured by that particular service. Again, this is a naive implementation of a load balancer. It's going to forward that traffic to any healthy instance, regardless of where the source of the traffic is coming from. Let's talk briefly about why that's such a hard problem, or why that represents kind of an interesting challenge, right? What this represents in Kube-proxy's case is like simple L4 load balancing. It's like really simple in that it's not trying to be super smart about understanding the load of any particular endpoint. It's just trying to balance its traffic across the set. And there are two implementations of how Kube-proxy does that. It tries to do it with IPtables and with IPVS. And we haven't explored the IPVS part. That's next. But what we've explored so far is the IPtables part. So because of that, because it is somewhat naive, it means that like whenever a service is defined, whether it be cluster IP or NodePort or any of the other type of services, except for external DNS, that one has nothing to do with Kube-proxy. But cluster IP, NodePort, and load balancer, all three actually do configure, are configured by Kube-proxy or implemented by Kube-proxy. That there are some knobs and dials, things like external traffic policy, that allow you to define exactly what that behavior might be. Before we get into the exactly what those knobs and dials are, I really want to talk about external traffic policy local. But first, I want to make sure that we understand why the difference between these things real quick, right? So we talked about kubectl get svc nginx show YAML. So cluster IP YAML. Cluster IP and NodePort are really pretty darn similar. Right? We can see that both the cluster IP is like the default type of service that will be defined if you don't specify anything else. Cluster IP will actually represent an instance of, will get an IP address from that services CIDR that you configure for the cluster. In our case, we configured 1096.0.0/16. So we'll just randomly pick an IP address from that range, and it will hand it off. And then it will actually handle any port forwarding or port mapping configuration that's necessary, and it will kick back to your service, right? So that's the default service. If you just do kubectl create service, you're going to get a cluster IP service. That's what it is. But let's look at how that compares to NodePort. So in NodePort, the way it's configured, right, we still get a cluster IP. Even though I didn't ask for a cluster IP, I always get a cluster IP. Except for one particular case. So in the way that NodePort works is that I'm also going to get a NodePort. And this NodePort will be taken from a configured range on Kube-proxy where we specify the NodePort range. And that NodePort range by default, if you don't specify anything else, is going to be port 30,000 to port 32,767. So you have 2,767 ports to use within that range that are going to be expressed by each of the Kube-proxy instances. Again, consistency, right? So that service has been defined with that port. That means that port range that we just described, 30,000 to 32,767, it's going to be configured consistently on every node running Kube-proxy. It means we have a flat port range that is defined consistently on every node running Kube-proxy. And when a node port has been granted to a service, regardless of which node you go to, you're going to be able to see the result of that service. And that's actually one of the things I wanted to show. So if I do kubectl get nodes -o wide, if I do curl for each of these hosts, right? Regardless of which host it is, 7, 6, and 5, regardless of which host it is, I can actually target that service. Because Kube-proxy is configuring IPtables on every node where Kube-proxy runs consistently. Now what it means is that if I were to hit that control plane node, because my Nginx pod would never land there, it would mean that I would get a consistent source address, because I'm never terminating on a node where that node is actually existent. So it's interesting stuff. So Kube-proxy configures that port range, port 30,000 to port 32767, consistently on every node where Kube-proxy runs all the time. And by consistently, it means that like some nodes may take longer to actually implement the change depending on the scale of services that we've defined, but each of the nodes will have that consistent view of the world. All right. So, cluster IP, no node port. It's only used within the scope of the cluster. And what's interesting is, because we were just looking at the IPtable stuff, if you look at the way that the IPtable stuff is doing its magic, it's doing its magic by manipulating the packet, right? It's not necessarily, IPtables is not, the cluster IP address is never something that is expressed as a routable IP address within the overlay network. It's only routable in that there is actually some manipulation that will happen by IPtables to make sure that the destination IP address is munged to one of those healthy endpoints described by the service. Let's talk about that real quick, because I want to make sure that we understand what I'm talking about there. It's a little confusing. So what that means, right? We have our cluster IP, right? Can I ping that cluster IP? Shoot. Apt install ping. What do you think? This one? Yeah, totally. So, now this is an interesting point. Can I ping the service? I cannot. I can never ping a service of cluster IP. Does that mean it's down? Does that mean it's not working? No. The service is up, but I can't ping it. And that means, like, as a network engineer, that was really confusing to me, because I was like, well, why can't I ping it? It's an IP address that seems like it should be available on the network. It's a cluster IP. The reason for that is because that cluster IP it doesn't have an ARP either, right? If I do ARP AN grep 1098.245, oh man, IP nay show. There's no ARP entry for that either, because it's actually only implemented inside of IPtables. It's only implemented by, basically, if the source packet, when the request comes in, when that TCP request comes in, right, we're going to look at the source and destination IP address. If the destination IP address is that cluster IP, we're going to manipulate that packet and change the destination IP address to one of the healthy backends based on that randomizer that we saw earlier in the IPtables output. So a brand new TCP session comes in, its destination IP address is 1098.206.245. Before that packet leaves the host where Kube-proxy runs, the destination IP address will be different. It will be one of the healthy backend pods, pod IP. Yeah. IPtables save, grep nginx. So this is our nginx service. Right, so here we are balancing across the backend services. And for each of these statistic lines, we're going to see a different IP. Right? So that one's going to forward it to 1044.1.3. The next one, which is going to take statistically 33% of our traffic probability mix, is going to be 10.244.1.4. And the next one is going to take 50% probability random mix. It's going to be 10.244.2.3. It's kind of crazy cool stuff, but like that's actually how we're balancing this traffic back and forth between the 3 points, between the 3 backend healthy points. And if I were to do IPtables on here, or sorry, TCP dump, if I were to do TCP dump on here, I would be able to see that that packet had been manipulated before departing, right? Even though that my request came in from, even though my request is coming in and my destination IP address is that that cluster IP address, that 1098 address, before it leaves this node, the destination IP address will be one of the resolved IP addresses based on whether they're healthy or not. Good to know and good to understand how Kube-proxy actually does what it does. All right. Now, we've talked about NodePort. We talked about how NodePort is effectively the same as cluster IP, or the different services, right? We have a service of type cluster IP. We have a service type NodePort. The difference between NodePort and service IP is that when we have a NodePort, we're grabbing one of those ports from 30,000 to 32,767, and we're expressing it as yet another possible source, right? So in this output, we can see that there's actually these 2 lines up here at the top, right? This is the implementation of a NodePort service. These NodePort services, right, are going to have a destination port saying, if you're coming in and your destination port is 31962, then kick it on over to the service that is going to handle the balancing between all of the healthy backend points. Those probabilities do look weird. I agree. But it's the random thing that actually puts the skew on it. And yeah, it's totally bizarre. All right. But if I look at just the nginx one, I don't see that destination port. That's our difference, right? So if I do pull that up and then pull up this one. So the top one here is actually our NodePort implementation. And the bottom one here doesn't have a NodePort. Wait, oh, my bad. Hold on. There we go. Ah! So there's NP. There we go. That's what I want. So there's my NP. So I can see these 2 NodePort lines here, which are actually mapping traffic back to my service. And then I also see the Kube service defined for the cluster IP associated with that guy. And then, but my non-NodePort instance, right, only has the cluster IP. It doesn't have the NodePort associated with it. Now, what is the difference between NodePort and load balancer? Does anybody know? Anybody have any ideas? Difference between NodePort and load balancer, service type load balancer, and service type NodePort? Before we proceed with that, I want to actually point out something that I thought was really interesting when I first started playing with Kubernetes and trying to understand services. Load balancer isn't a built-in thing. So by default, it means that like if you have a Kubernetes cluster, you may not actually have a load balancer implementation. You can still define a service of type load balancer, right? I can do that now. kubectl create service type load balancer. Nginx LB TCP 80. Oh, run. Okay, so I have my three services, kubectl get SVC, right? I have Nginx, Nginx LB, and Nginx NP. I can see that I got a cluster AP each time, and I got a different node port for the bottom two. So I got a node port when I described a node port, and I also got a node port when I described load balancer. Correct? Mostly correct, yeah. LB is a node port on steroids, exactly. Good answers. All right. So, load balancer is money. Absolutely correct. All of those things are true. Well answered. Load balancer can be offloaded to data plane. I'm hoping that's data plane. Yeah, so load balancer is money. Load balancer is node port on steroids. And load balancer for cloud providers or managed infra and node ports for local development machine provided ports, mostly true. Okay. So you're always going to get a node port. When you create a load balancer, you're actually interacting with some other system, whether it be the cloud integration provider or whether it be like something like Metal LB. You're actually going to interact with that system and say, and request that they configure a load balancer on your behalf and point it back to all of the nodes within your cluster, because we understand how that traffic path works, right? So because we have a node port, we're going to have that load balancer forward traffic back down to our nodes on that specified node port, and our Kube-proxy is going to balance traffic across those pods. Load balancers are L4 mechanisms, layer 4 load balancer, right? And that means that we don't have any guarantee that the path back to that service is going to have to try and retain the source address. It means that this traffic might come into one of the nodes where that service is and terminate on that pod, leaving the source IP address in place. Or it might come into that node and traverse to another node because of the way that the IPtables forwarding works, meaning that now the source IP address is that first node before terminating on that service. Now I think it's time for us to talk about external traffic policy real quick, because I think it's actually pretty interesting. So one thing I do want to talk about, though, is like, because in my cluster I don't have a load balancer implementation in place, I'm never going to see it resolve, right? So because I've actually asked for a load balancer to be created, that's never ever going to happen because there's no load balancer implementation inside of my kind cluster right now. I'm not running in the cloud. I'm running on a kind cluster brought up locally on my machine, and I haven't deployed anything like Metal LB or any of those things. And so what that means is that's not gonna work. I'm not gonna be able to actually ever resolve that to a load balancer IP. If you see this in your environment, it may be that it means that you're like on a bare metal configuration, or that the cloud provider integration isn't working, or that, you know, whatever it is that would satisfy that load balancer implementation is not working. How do we get real IP in that case? Let's talk about that. This is the part where Bogdan is actually going to talk about. Yep, it will get up. Let's see. All right. SVC, NodePort, Nginx, NP. So there's this line, which is defined by external traffic policy cluster. So what happens if I change this to local? So now my external traffic policy is set to local. Now, well, you know what I should have done? I'm actually going to put this back to cluster IP, or cluster. And then I'm going to go to tab 3. Now I want to do grab. All right. It's going to happen quick. So we're going to have to like local. Changes. So now what's happening is that we have a new line that describes if the source is coming from localhost, then it's headed for dport. Source type local. So understanding whether the traffic is actually coming from local or somewhere else. So when I actually change that external traffic policy, there we go. When I change that external traffic policy, I change the way that the behavior would work. So you remember earlier we did a curl against each node, right? So we have, let's do this. So kubectl get nodes for I in 172 dash O wide for I in 172.17.0 dot 5 to 7 do echo $i done. Looks good. Okay, so then we want to do curl $i, colon, and then the port of our cluster, of our node IP, or our node service, our node port. We'll just do grep requesting. Done. Now this is kind of interesting. Wait. Let's just do this one at a time. So curl 172.17.05. .31962. That works. 6. That works. 7. Nothing. Isn't that interesting? Let's go back to 5 and see if the IP address changes. It does, right? We go 2324, 2324. Let's go back to 6. See if the IP address changes. 1314, 1314. At the moment, this is actually balancing okay, right? So kubectl get endpoints nginx np. So we have all 4 of our hosts, or all 4 of our pods are being deployed across 2 nodes. I wanted to see where they're deployed. Let's check that out. So kubectl get pod -l run equals nginx -o wide. Right? I have 2 on worker. I have 2 on worker 2. Here are their IP addresses, right? They're broken up by IP address. And because there's 4 of them, 2 on each node, my balancing is actually still going to work out okay because the traffic will be balanced across each of the 2 inside of that host. But let's talk about what's happening here. If I do if I do the control plane node, which is which is IP address 7, I'm not getting anything back. What do you think a load balancer would do if it didn't get a reply back from an endpoint like this? Right? It would determine that node was not in the running. It was not a healthy backend service, and so it will take it out of the routing decision. Right? The load balancer on the outside, ELB or what have you, when it tried to connect to this host, it failed, and so it will actually take that host out of the list. That means that the only hosts left in my cluster that can answer that question are worker and worker 2. Now, worker and worker 2 at the moment represent a set of 2 pods on each of the 2 nodes, right? That means that they're still in the running. The load balancer out front is still going to balance between those 2 nodes. But what's going to happen when the traffic terminates on those nodes, right? Now what happens is that we're actually going to be balancing back and forth between only the 2 pods that are local to that node. We're never going to actually egress the node and go over to the other node. We're going to keep it local on that node. And the same thing if I go back to the other worker, right? I'm actually only going to balance this traffic across the 2 nodes that I know, the 2 pods that I know about locally. I'm never going to allow that traffic to leave this node and go somewhere else. This greatly simplifies the traffic pattern because it means that when the TCP connection comes in, you're terminating on a host, and your source IP address will always be the same because we know what that path looked like. We're never introducing an extra hop like we do in cluster mode, where if the service isn't local, or if by chance you pick the random, we decided to route your traffic over to another node, we're going to change that source IP address. We keep it local, and it means that the source IP address is stable, and it means that you understand the traffic pattern better, but there's a problem. Let's talk about what the problem is. Scale, deployment, nginx, replicas 3. Get endpoints, nginx, well, let's do describe. So now I only have 3 pods. And these pods, there's 2 of them on worker, and 1 of them on worker 2. Does the load balancer know that? Does the load balancer know that the availability is different between the two workers? It does not. It has no way of knowing that. So it's still going to load balance using its algorithm across those healthy endpoints, the nodes. But the difference is in the availability. At the moment, I have more availability on node 0 than I do on node 1. But the load balancer doesn't know that, so it's going to just balance across the two of them evenly. There's no OSPF here. This is basically just handling a percentage of routing back and forth between the two. Okay. For cloud providers or managed, yeah, okay. So the master is not tainted, it just doesn't have a pod. If I put an Nginx pod on the master, it would start answering. And the master is tainted, sorry, yes. The master is tainted, so that's why it doesn't have a pod. All right. Lots of information there. And we've explored quite a lot into the IPtables thing. We explored theory of operation. We talked about how it works. We talked about what Nginx is, what Kube-proxy is trying to do here. A couple other things I wanted to share about with Kube-proxy. So, tables worker bash. Whoops. Interestingly enough, we need to know the host name. The reason that Kube-proxy needs to know the host name in its configuration is so that it can determine what local traffic is. If that is misconfigured, if Kube-proxy doesn't understand what the host name of the node itself is, it has no way of like deducing what the local traffic is, and that means that it would not be able to handle things like external traffic policy local. But that's how it's determining it, right? It knows what local is because it knows what the host name of the host is. And from there, it can determine what the source IP address or the actual IP address of the host is, and then it can actually kind of determine from there, like what is local traffic, what is not local traffic, and how to manage that problem. A couple other things about Kube-proxy. Let's do SS minus ANLUT, well, LNUTP, LN tulip, grep Kube-proxy. This is a great way of actually understanding what a particular service is exposing or what it's actually listing on, right? And so we can see that Kube-proxy is listing on all ports on 32018 and 31962. These are our node ports that we've expressed, right? That makes sense. We can also see that it's bound locally, localhost 10249 and port 10256. So if we go back to our reference for Kube-proxy, we do Control F 10249. Right, we can see that 10249 is the metrics endpoint. Right, so let's go back to here and we can do curl localhost 10249 or 127.0.0.1 10249/metrics. Oh, heck. So these are the metrics exposed by the Kube-proxy. Yeah. So here are the things that are exposed by the metrics endpoint for Kube-proxy. It talks about a lot of the standard Go stuff, and then it starts getting into things like that are HTTP requests that it saw. It talks about network programming. How long did it take Kube-proxy to configure the network? And compared to other things, these are like quantile buckets, right? So we can see that most of them were taken in about 65 seconds. Seems kind of slow. We can see sync rules, how long it took to actually download or sync the rules with the actual configuration. We can see changes pending and how many changes total there were. This is how many changes we've seen against Kube-proxy, which is interesting, a lot of changes. We can see the sync proxy rules latency, how long it took to actually do these things. So all of these are metrics that are exposed. So if you're trying to understand the behavior of Kube-proxy over time, definitely some good metrics exposed there. We also have a config-z endpoint, 10.256, right? So I'm actually going to do the same thing I showed you last time. kubectl get pod-n kube system kube. I'm going to jump into one of these and pull the config-z, right? So kubectl get raw, actually get pod-n kube system -o yaml grep self. I'm actually really sad self-link's going away. Like this might be going away soon because they feel like it's kind of a tough implementation to support. But it's still here for now, so we're going to keep using it. Kubectl get raw. $10.56. All right, fine. Docker, let's just go, let's do it a different way. Exec in, I'll have to figure out what the right incantation there is. I believe that, oh, you know what, I don't need the slashes, that's what's happening. Do we name our ports? Oh, snap! We're binding to ports, but we're not telling people we're binding to ports. That's kind of janky. All right, probably going to fix that. Tables, control plane, bash. So if I do curl 127001 10.256 config-z, wait, hold on. SS-ln tulip. Grep proxy 10.256 curl HTTPS. So it's healthy. That must be just the health endpoint. I wonder if we're expressing config-z on the, does Kube-proxy have a config-z endpoint? I thought that it did. It does, okay. I was just looking in the wrong place. All right, so there is a config-z endpoint on Kube-proxy. So we can actually hit that thing and see how it's configured. These are the configurations of Kube-proxy for this particular instance, and we can actually interact with it without a cert. So that's cool. So if we go back to our kubectl get raw, 10.249. Yeah, it's because the port's not actually exposed that way. So we can actually get this information, which is pretty handy to understand like how it's actually configured at runtime. We can see how it's actually configured at runtime by looking at the pod, right? So we can actually understand what configuration it actually had, right? So kubectl describe pod-n kube system Kube-proxy jf. And then the config map that represents Kube-proxy. So kubectl describe config map -n kube system Kube-proxy. Here's the configuration of Kube-proxy. Setting the metrics bind address to localhost, and all of that actually enabling DSR false, setting the network name, source VIP, all that stuff. These are all flags that you can use to configure it, like what the resource container is going to be put in, what the port range is. Because it's not specified, it's default 30,000 to 32767. Because mode is not specified, mode by default is IPtables. And then how it's actually going to use and how it's actually going to authenticate is using a service account. So its kubeconfig is defined using the token file service account token. That's actually how it's going to authenticate to the API server so that it can do its watch and understand, right? So like it's the entire configuration of all of the kube proxies is shared across that whole set, and it's expressed here, right? So what its bind address is, the client connections, the cluster CIDR is configured, contract is set, the health Z endpoint, hostname override, no need. It's actually configured correctly already. Here are just some generic settings for IPtables and IPVS. And these are the configurations of all of these bits here, right? So it has a config-z endpoint. That is how it's configured. We've talked about, let's go back here and make sure we talked about how it's authenticating. We talked about IPtables. We talked about services. We talked about theory of operation. We talked about config-z and metrics. The next thing I want to talk about is IPVS, and then we're going to wrap it. So what time is it now? Let's make sure that we're not like super way over time. Oh, it's 3. Okay. Let's do IPVS real quick, and then we're gonna call it. Okay. Press clear. Okay. I actually already have an IPVS cluster up, so that'll save us time. Kubectl get nodes. Kubectl get pods. Nothing, right? So kubectl run nginx image nginx replicas 3. Kubectl expose deployment nginx port 8080, actually 80. Oh, darn it. So here we have our services that we've already defined. So we can do kubectl get endpoints. We can see our two services are configured identically. All that stuff's in place, and that's all working. So now if I do curl against one of the IP addresses, 172.17.03, it'll get SVC wide. We can see our nginx instance running. all that stuff's working. This is an IPVS cluster. I want to talk briefly about how this was configured. This is kind of interesting from the kind config perspective. If I look at the configuration of this file, this is a standard kind config, but I'm populating the Kube-proxy configuration and setting mode to IPVS. So this is actually how, the only difference between the configuration between the other cluster and this cluster is that I've set the mode to IPVS for Kube-proxy. That's all that was necessary to do, right? And so now if I docker exec into my IPVS worker, and I do IPtables save. We've all seen this command a few times now. Whoa, I don't see one. That seems weird, right? I should actually see something there. But I don't. So where is that configure? Install vim. How do I actually understand the configuration of it then? Right? It's interesting. Do I still see that NodePort bound? Let's take a look at that real quick. So SS minus tulip. I still see the NodePort bound by Kube-proxy, right? But when I look at IPtables save and I look for Nginx, I don't see it there. Yes. Bogdan, you're like my favorite viewer. You're like totally ahead of me. Help. So IPVS ADM-N. So I want to see -L. And here we can see that we have we're round robining port 30895 across these three hosts toward those target IP addresses. We're round robining 10.6.106 72.22.22 across these IP addresses. Right, so we see our service, we see our cluster IPs being round robined against these things, and we also see our port in the output as well, right? Yeah, because it's trying to resolve host names. That's why it's taking so long. So in this output, we can see that we're actually using the IP. Yeah, let's do IP. Well, why not? L and the same. All right. So we can see that, you know, we have a bunch of IP virtual servers configured, right? And we can see how they're configured. We can see they're configured all basically in a round robin mode. we're going to see that, like the cluster IP address that we have associated with things, or the node port, we're going to see actually balancing across things. So in this case, it's a node port. 30895 is the node port we have for Nginx service, and it's actually going to round robin against these 3 entries and forward back to that service, right? And if we look at the cluster IP, here's the cluster IP we have associated with one of our services, the same round robining, right? You can see that we don't have any active connections and the weights are all equal. A lot of this stuff may be configurable in a forward version of services. We're looking at trying to annotate services in a way that you can actually specify the load balancing algorithm that will be used by IPVS. But if you think about it, it's sort of diminishing returns because you would be configuring them, and each of the instances where Kube-proxy runs would be handling the configuration of IPVS ADM. It wouldn't be a consistent IPVS ADM configuration across the set. It would be each of the implementations of them might be subtly different. All right. So again, the weird thing about IPVS mode is that the IP tables look dramatically simpler, but they don't do nearly as much work as they do in IPtables mode, right? There's way less stuff happening here. What's happening here right now is basically just like standard rules and configuration that Calico puts in place for things, but there's no, there's some kube forward stuff, making sure contract stuff gets picked up. Making sure the forward check stuff gets picked up. But there's not a lot of the same stuff that we saw in NAT. You can see that in the NAT table, like some of these things are defined, but not a lot of them are the same, right? Like we don't see as much in mark mask. We don't see as much in NodePort defined here because that's actually going to be handled by the kernel now because we're actually configuring IPVS directly. All right. kubectl logs. kubectl logs -n kube system kube proxy xdg, right? So here's some logs from the Kube-proxyer. It's actually just saying that it's configured with IPVS and scheduler not specified, so use round robin by default. It's setting up some syskettles. It's waiting for the caches to sync, and then it's basically just watching for endpoints and again configuring these things. So for your purposes at this time, they're equivalent, right? IPVS and IPtables are doing this, the 2 modes are doing effectively the same work. IPtables came first, it's still the default. I'm actually not sure when the IPVS may become the default, but I know that for your particular purposes right now, they're equivalent. And if you wanted to actually explore using IPVS instead of IPtables, that is available to you today. I think what's interesting, one of the things I'll say before I also bounce is that the difference between, so IPVS mode, in my opinion, was one of the early attempts to try and fix one of the major problems that IPtables kind of had with relation to the problem of IPtables, right? What we talked about so far is let's kind of level set on IPtables real quick. IPtables was built like way back in the day, and the idea of IPtables was that it would be configured, and then you would not mess with it, and it would just handle like all of the TCP flows coming into the system, and that's why it being not atomic, as we mentioned earlier in the schedule, wasn't really a big deal. Because we're using things like Kube-proxy and we're beating up on IPtables, there's creating an incredible amount of churn in IPtables for the cluster. Because we have things like Calico and Canal and Weaveworks and like anything that's actually going to configure network policy on your behalf, configuring IPtables. Because we have Kubelet configuring IPtables. All of these things together mean that we're actually doing quite a lot of churn to that IPtables configuration, and it causes things to behave in ways that are maybe not the best, right? Because it was never really meant or designed for that. NFTables is a step in the direction as well, right? Where we're like, you know what, we know we got to get better at actually having a dynamically configurable filter system. So NFTables represents, you know, a horse in that race, right? So we have IPtables old and kind of, and it has lots of interesting sharp edges when there's a lot of churn. NFTables solves the churn problem, but also introduces some interesting problems about the migration from old to new. Then we have IPVS. If we're going to do load balancing, why do load balancing with IPtables? Maybe we should use IP virtual server for that. Another horse in the race. Then we have things like Cilium, where they're like, you know what, like we can just do all of this in XDP and BPF. We don't need to be doing this in, you know, some of the older technologies like NFT and those sorts of things. Although it's interesting, if you look at NFT closely, it's like effectively still implemented in BPF. So all of these things are converging on like ways to make all of the problems that Kube-proxy represents better, and generally in Linux. It's not just there's not just one way to solve this problem. There are lots of ways to solve this problem, and I think that they're all kind of converging on making things better. And so, yeah, that's true. Is there a way, so I was saying, yes, that's true in that IPVS's smallish clusters are pretty good. IPVS does have a limit for the number of services. For example, in OpenShift, it has a limit of 4 bracket 10,000. I don't know what number that represents, which IPtables would hit that. That's true. As you grow the number of services, IPtables, obviously because of the points I've already described, right? As you grow the number of services, you have more churn, which makes IPtables fall over faster. Because it's not atomic, as you grow the number of services, the time it takes to actually handle the reconfiguration of IPtables takes longer, right? Because it's not atomic. But would you be able to move to IPVS and get away from that problem in IPtables? Probably, because you'd be greatly reducing the number of things configuring IPtables on your behalf, right? You'd still have a bunch of rules that are being defined in network policy, but you wouldn't have as many rules that are being defined by things like routing, because those are going to be handled by IPVS. Is there a way to configure Kube-proxy to favor the same node ports or the same AZ pods? I don't understand the question there. All Kube-proxy instances use the same node port range, 30,000 to 32,767. I think what you're referring to perhaps is like topology aware stuff, and that's coming, but it's not here yet. Endpoint slice is a part of the topology aware work. If you're curious about that, there is actually a KEP topology aware Kubernetes. Oh, that's volume provisioning. There we go. This was done by Jundu. So there's more to be done here. But yeah, like topology aware, there we go. That's what I'm looking for. There is an enhancement proposal in place to try and solve this problem, like service topology, where you can actually handle things like topology aware routing for services. I think that's what you're looking for. I'll go ahead and put it in the notes so we don't lose it. And then I'm going to sign off. All right. Thank you for digging into this with me. There's so many interesting things that we're going to be playing with in the future versions of this. So far we've done Kubelet, we've talked about Kube-proxy. In the next one, we're probably going to talk about controller manager. We're going to talk about Kube-scheduler. We're going to dig into some of the details about how all of those things work and some of the concerns around how all of that stuff happens. But the big takeaway for Kube-proxy, again, I feel like what's really interesting to understand is that Kube-proxy does a lot of the heavy lifting for services, and that it is actually a set of pods that run on your nodes, so each node has its own consistent and unique view of the cluster surface. So thank you again, and you all have a great killer weekend, and I'll see you next time. So thank you, thank you, thank you. All right. Whoop. We'll go back to face. And yeah, have a great weekend. Thanks so much for your time.